Hello, in this first video I'm going to be introducing issues related to reliability and validity. So the purpose of the validity review is to cover a series of topics. Construct validity, which includes reliability and validity of a measurement. In this video specifically, we're going to focus on issues related to reliability, of a measurement. And then we'll cover internal validity of a study, external validity of a study, and finish off with conclusion validity. So when we talk about reliability, and most of this hopefully should be a review to you, reliability is a stability or consistency measure. So I tell most students to think of consistency when they think of reliability. This can be consistency across different times, different questions or tests. So even within a single test, you want the same test to consistently be asking you about the same content. Different observers, this could be multiple research assistants, this could be multiple teachers, or other methods of assessment. You want to choose a statistic for the assessment of reliability that depends on the type of data. So if you're an exercise physiology student, the measurements you're going to be using for reliability could be different than those if you're a sports psychology student or a teaching administration student. It really depends on what type of data you have and what type of reliability makes sense. There are some measurements that stay very stable for very long periods of time. In sports psychology, we think of things like personality as a very stable measurement. You can expect similar measurements, 6 months apart, whereas in some situations you can't expect, you wouldn't expect other things to be the same thing. And again, using sports psychology, you wouldn't expect group or team cohesion to be the same, even 24 hours apart. So you have to kind of think about different ways to assess reliability under different situations. A second definition that can be used especially in the lab setting is precision. Scores are free from errors of measurement. So precision is sort of like right on the cusp between reliability and validity. It is defined under reliability, but it has some components that might make you think of it as validity. So I tend to think of it right in the middle there. What we're looking here is for unsystematic errors, random or unexplained variance, and compare that to systematic variance, which is variance that can be estimated as a part of differences in trials, days, scores, equipment calibration, radar effects, and so on. So in order to provide an example, I'm going to use or demonstrate something called classical test theory. And this will hopefully help you understand the statistical theory behind reliability. For one individual, they have a true score, which would be, at best, estimated by the mean of all repeated trials. Think of this as somebody who stands on a scale, measures their weight, walks down the hallway, comes back to the scale, and does this 200 times. And the average measure of those 200 measurements would be essentially our best guess at what their true body mass is, because we know that scales don't actually measure weight. Then there would be always some error, because I laughed at my old scale. You could literally walk down the hall, come back, and it would be up 4/10 of a pound or down 2/10. So there is the observed, which would be the measure that you took, and then there was always some form of error in our measurements. So that would be the kind of standard deviation of that mean of 200 measurements on the scale, where you know that you're not going to hit the exact same weight every single time. Now this would also occur for just about everything. Anytime we take a measurement, we would have some sort of observed measurement, some sort of error. If in that 200 times we repeated it and we got the exact same weight every single time, there would be no error measurement. It just doesn't usually happen. Even our best calibrated measurements have some error. So the way that we can best estimate a true score, because also you're not taking anybody's measurement 200 times, you just don't have time, is we take their measurement once, maybe 3 times if it's a vertical jump. They take it, they jump 3 times, and we take the average of the 3, or sit and reach, same type of thing. Their observed score is going to be kind of guessed is their true score plus or minus error. The other way to state that, if we were to think of this algebraically, is that the true score would then also be equivalent to the observed minus the error. So we've just adjusted this because we know that we're never actually measuring a true score. What we're measuring is an observed score. Now, when we can calculate this through a repeated measures ANOVA, especially if we're doing multiple measurements over time between raters and so on, this component, notice, is going to be our numerator, the between subjects. The more heterogeneous a group, the higher the reliability. Now that sounds a little bit weird, but we need to be able to get groups across a spectrum. So what we have here is two things. The variance in the observed scores, so how different the groups are, or the group is, and then the intersubject variance, the variance between those individuals. So when we put those two things over each other, the bigger the numerator, the bigger the observed score, ultimately the bigger the between subjects mean square variance. We want this to be big because ultimately we're going to be using between subjects over within subjects to calculate reliability. We want, the bigger this number is, the better our estimate of reliability will be. Now, our denominator is going to be the mean subjects within error. This is our error variability. This measures the variability within a subject, right? And that's what we want to be consistent, is that the person within themselves is going to be consistent. A lower error term leads to lower intrasubject variability, so we want this to be small. A lower intrasubject variability means that we have more consistency over trials, or more precision. So if we have a lower error term, that means lower intersubject variability. Lower intersubject variability means more consistency. Ultimately, a lower error term leads to higher reliability. So we want mean subject within error to be low. We want mean subject between subjects to be high. Let's see an example of that. In this example, I'm going to do 6 trials. Nominal level of measurement. It's measured over time, but not in equal distant. We don't have a clear linear. We're just day 1, day 2, or so on. Skim folds here is my dependent variable. I'm going to use the 7-site measurement using skim fold calipers. If I actually did this, it would be highly problematic because I'm horrible with skim folds, but that's just me. And then I look at the repeated measures output. So if this case, let's, for the sake of this example, assume we have met sphericity and look across this line. We see that we have a significant difference across our 6 trials. That's problematic. We don't want statistical significance across our different trials. That suggests that we don't have consistency. So what classical test theory, now that just tells us the difference between our trials. Now let's actually measure the reliability coefficient. Going back to classical test theory, initially identifies that reliability would be measured as true score variance over observed score variance, where we have to estimate the true score using the formula we showed before, observed plus error. So then reliability then becomes observed plus error over observed. If you can follow that linear thinking, I'm going to show you what we're going to place in for each of for observed error. So the error part is going to come from the mean square error. So we go to the error term under the repeated measures, within subjects component, 11.43. And then here is that heterogeneity of our groups. We want this number to be very big, and you can see that it is in this example, 138.07. This is going to be our numerator. That is the observed plus error, or our intersubject variability. So if we could put the mean square between subjects, subtract out the error component, all over the mean square between subjects, we have a reliability coefficient of 0.917. Now, if you look up at one of the key authors to determine what adequate reliability coefficient is, Nunnally and Bernstein, this book was published back in 1974, and it's out of print. It's really hard to get a copy now. They said that adequate level for consistency was greater than 0.7 was adequate. You wanted greater than 0.8 to be good, and then greater than 0.9 was excellent. So 0.917, we're doing really well here. But remember, we had statistical significant differences between our trials. That's a problem. So we have two different numbers, and we kind of have to reconcile the fact that there are problems between the two. So we're going to take a look at a different option. If we look at our graph, we see where that inconsistency comes from. Over the 6 trials, we see the numbers go up, they're around the same here, they go up again, they drop down, so we see some consistency. Well, what happens if we consider trials 1 and 2 here? We're going to knock these 2 trials out as practice trials. And we just look at trials 3, 4, and 5, realizing that maybe 6 is a problem too. Now, this is what we have to kind of go back to theory, logic, and literature, where if we do just trials 3, 4, and 5 for our measurement, we see that now we obtain statistical non-significance, suggesting more consistency across our 5 trials, or our 3 trials. And if we take those the between subject variance and the error, and we take those calculations, we get 0.835. Now, we aren't as high as we were before, where it was 0.917, and we were in the excellent range, but we're still well above the adequate range. We're in that 0.8 area, so we're fairly confident that we have both a consistent measurement from our intraclass reliability, ICC, and we have it from our measurement over for our non-significance for a repeated measure ANOVA. So those two things put together give us 2 pieces of evidence that we do have good reliability and validity, or good consistency over trials. So that's an important component for us to consider. Now, this is what we call, this measurement is called intraclass reliability. Intraclass is a form of, or intraclass measurements, ICCs, is a form of measuring reliability that has taken over for Pearson correlation coefficients, where we know that the ICC is just a better measurement given its use of univariate ANOVA as opposed to a Pearson correlation, which is bivariate and would have only been able to measure trial 1 to trial 2, trial 2 to trial 3, trial 3 to trial 2, and so on. Could have only measured 2 trials at a time because of the bivariate nature. In the repeated measures ANOVA, we could measure all 6 trials, or we could just measure 3 trials at a time. So it is overall a better measurement in terms of being more accurate, allows us to deal with more sources of variance. If you go review my 610 materials under reliability, I talk about the intraclass coefficient at length, so that's worth checking out. When you're doing the math yourself, make sure you determine if the F ratio is significant for the trials. If so, you can compute R, but remember, we had those problems, then examine to run the repeated measures ANOVA to get non-significance. Again, now we have both a good reliability score and we had a non-significant R. Now, this is for a measurement study, not necessarily for a study where you are trying to do an experiment. Ideally, somebody who was doing something where they were doing a measurement study, this would help recognize that a researcher would need some familiarization trials before they start taking the official observed measurements. This would be part of the protocol that would be established for a measurement, not necessarily that you would just throw out 3 trials for the sake of throwing out 3 trials. It's very nerve-wracking, as we've talked throughout the semester, for just throwing out data for the sake of, for a data-driven purpose. You really want to make good, solid decisions. Alright, thank you very much. Please move on to video number 2.